All right. Thanks. All right. So 9:04. All right. So I just want to spend a few moments giving. I was really unfortunately not able to make this trip, but I really wanted to attend in person. But anyway, I'm going to just give a brief update on sort of current activities in the U.S. Climate Reference Network and kind of a status update. And I want to thank my cohort and colleague, Dr. Howard Diamond, who's the U.S. CRN Program Manager, for providing a lot of updated information related to not only our CONUS network, but also what we're doing in Alaska and Hawaii. So just a little bit of background. The vision of this network has been inception since 2004 with an overall goal of providing a sustainable network such that with confidence we can quantify how the climate in the U.S. is changing over the next 50 years. And that is through the primary variables of precipitation and temperature, soil moisture, and soil temperature. And with these, the thing that makes us unique about this is that we have triplet measurements. If you have one measurement, you don't really know unless you measure next to it if it's right. If you have two, you don't know which one's wrong, but three gives you a pretty good idea when you have a bad measurement. So the triplet idea is really critical to what we do in the USCRN. All right, so a little bit of background about our national coverage. We have approximately 114 stations in the lower 48, 13 of which have soil moisture and soil temperature information. We currently have 23 stations in Alaska, 2 stations in Hawaii. And at one time, there was to be approximately dual stations for every location. So that in the event that a site may go down for whatever reason, there would be a backup. But that only actually occurred because of costs and things like that. So we only have like 7 dual stations over the whole U.S. We are entering our 3rd decade of operations, and because of COVID, we weren't able to get much in the way of any installations done in Alaska. But we are going to be getting 2 new ones put in actually this month. And we've actually got a couple, and I'm going to show a little bit of data because we recently got it from a couple sites where we're trying to do some soil moisture and soil temperature in Alaska. So the value is one of the things that we're generating. This is what we're calling it a national temperature index, and this is being generated from NCEI. And this is looking at the average with regard to the temperature anomalies over the course of the whole year. And you can see the numbers agree very well with what they determined from the numbers that come from the climate division. We like, again, I want to stress the fact that we're the only reference national network because we have triple redundancy. We provide a basis for other mesonets to compare against. We have hourly soil moisture and soil temperature data that are part of NOAA's Meteorological Assimilation and Data Ingest System, known as MOISST. And that makes it available for models to either potentially be used for data assimilation or for real-time model data comparisons. And this data is currently being tested against some of the UFS modeling systems. And also the data has been used for satellite CalVal for some of the NASA SMAP missions. Again, I want to stress the triple redundancy. This data is actually hourly, so it provides a really rapid response to precipitation events. We are also contributing to the International Soil Moisture Network program, and that's stationed in Koblenz, Germany. And again, I mentioned that where we're providing the data to MOISST. Okay, next slide. So basically, this is what a current U.S. CRN station looks like. So the primary measurements are aspirated temperature measurements at 1.5 meters. We use the MET1 shields for that. We also have 3 vibrating wires and all precipitation weighing gauge. And these are what the shields look like. They're pretty good size. They have a fan that provides a continual aspiration. The secondary measurements includes solar radiation, relative humidity, also land surface temperature, and wind speed at gauge height in order to make any corrections for solid precipitation due to the fact that in windy conditions, we don't do a great job of getting all the precip. Most gauges don't get don't have good wind fencing, so we have to correct the data. So this is where the solar is. That's where the aspirated or the relative humidity is in one of the shields. And then we have a downward looking IR sensor. And then over here is a cup anemometer for wind measurements. We have 3 separate profiles of soil moisture and soil temperature, 5, 10, 20, 50, and 100 centimeters. And these are about 15 feet apart around the south side of the tower. And then the stations can also be powered either by AC if it's available, or we can also do wind and solar in some cases. I want to stress the importance of really getting good measurements. I just want to spend just 30 seconds on this. The fact that this looks at accumulated precip over basically a 1-year period from various combinations of wind shields and precipitation gauges. And you can see an unshielded gauge catches about half of the precipitation that should have been. And so when you're doing soil moisture and soil temperature, you really want to make sure, especially if you're in a region where you get a lot of solid precipitation, that you're either using good shielding or that you can correct that data with a lot of correction algorithms if you have a measure of temperature and wind speed at 10 meters or even at half that height. And so if you need information on how to do that, John Kokendorfer, my colleague in Oak Ridge, has published several papers on this and provides really useful information of how to correct your solid precipitation measurements. One thing that we recently have done is we looked at potentially a smaller shield. We call it the low porosity double fence. And we tested this shield out against our CRN measurements at 3 different locations: Marshall and near Boulder, up at Niwot Ridge, in the mountains in Boulder, and at Chatham. And we did this because these are the 3 most windy sites in the US CRN network. And I'm just going to show you one accumulated precip where we compare the small double fence, which is what we currently have. This is a 27-foot diameter fence against the low porosity double fence, which is only 12 feet across. And you can see we got really good agreement. And this is a much more sustainable type fence for the long term, because we can actually use small little chain link fence sections to construct it. Currently, we are also transitioning to ACLIMA TDR probes in the soil network. We're going to be using one of 2 ACLIMA probe configurations, and that's going to depend on the typical soil bulk electric conductivity for that site. For sites with really high electric conductivities, we're going to go with a shorter configuration probe, either the 305 or 310W. For all the other sites, we'll use the 15 centimeter probe, the TDR 315N. So this because over the time we've been running these, there are just some soils where the bulk electric conductivities can really have an impact on the overall determination of the dielectric, which is how the soil moisture in these particular probes are determined. We've also are experimenting with a couple different sites in Alaska to obtain measures of soil temperature and soil moisture. Because of logistics, we thought we would at least experiment with the soil view probe from Chemical Scientific. This particular probe is an SGI 12 based. It outputs volumetric water content, soil temperature, the dielectric, and conductivity. And we use basically the 15 centimeter probe at a couple different sites. So we were able to get 2 probes at 2 sites in the southeastern Alaska region. This is actually data not from Alaska, but from an installation we've had at Crested Butte, Montana, in the East River Basin. But this is using the soil view probe at a location that's at 1,000 feet, and they get a heck of a lot of snow. And so these are two probes that are located within about 15 feet of each other. And this is looking at the volumetric water content at 5 centimeters over the course of almost a whole year. And surprisingly, I mean, I thought the agreement was actually really pretty good, given the nature of the heterogeneity of the surface, that we really got some pretty good agreement. We also got a pretty wide range in terms of water content, ranging in some cases when we had precipitation up near 40%, and then actually going down to almost near zero later in the fall when things were really drying out. So but with these probes, one thing that we can attest is the fact that you really have to be careful how these probes are installed, and really have to make sure that you ensure contact on those waveguides, especially in the upper part of the probe. So it's really critical with this particular probe. So this is some actual data we actually just got from Alaska recently, and this is one that we pulled out from Port Allsworth, and this is looking at the temperature at 50 centimeters over the course of basically a whole year. And you can see that overall we're really getting some pretty nice agreement, especially during the late summer, early fall, and in the wintertime. But there seems to be a little bit of a bias difference, or a difference between the two different probes, mainly because of location, I'm sure, but it's only on the order of about 1.52 degrees, which is really pretty good. We have just begun starting to look at the soil water content, so we hope to report on that at some later date. Another thing that we've done is over time, because of all the information that we get from these probes, is we've developed an SDI-12 hub. This hub provides an electrical interface between our data logger and 15 SDI-12 probes. And these all work with the Stevens Hydra Probe 2 and the Acclimas. They have self-resetting fuses, and so if one particular probe goes down, it doesn't bring the whole SDI network down, which can, as you know, if you work with these probes, can happen. It also has some suppression when it comes to some electrical transients to help keep any kind of surges down. And we also provide one-touch programming, and where you touch the one button and it will initiate the probe into a programming sequence, and it'll program all the different probes that are hooked into this with their own addresses, so that they can actually be, so you can read the different signals from those probes. And we've been recently working with Oklahoma Mesonet folks on sort of integrating the Terrell's probe, which is an SDI-12 probe, into this particular board. One thing that just came out last month, I just want to highlight, is we were using the data from the U.S. Climate Reference Network to identify biases near and subsurface meteorological fields, mainly air temperature and soil moisture. And we were comparing some of these data over the domain of the U.S. against some of the model outputs from the rapid refresh model out of NOAA, where it was simulating air temperature and surface temperature. We noticed that there are some, the model tends to underestimate soil moisture when the water contents are above 20%, and it overestimates when the water content is below 20%. We think it's how they actually parameterize the soil and the model conditions in this particular model. One last thing, we are adding some new solar and wind sensors to approximately 20 sites eventually in Texas and California in support of wind energy forecast. We want to use the Delta T SPN1 pyranometer, which actually gives you a learning cloud properties, and we'll also be direction for data simulation and modeling and comparison. And then we're also going to be taking a deep dive into sort of our paired sensors in Alaska with respect to soil temperature and moisture during using the soil view probes. And that's it.
Well, thanks, Tilden. We can try to do a question virtually, if anyone has one. It's a quiet crowd. Tilden, are your SDI 12 breakout boards, are those like available for purchase? How does that work with NOAA?
So we actually can send you, and we've done that. We've sent a couple boards to the OU folks, but I think these are boards that we actually send out and then have them made, and then we put the components on them. So it's something that we've designed and have shared and are willing to provide, you know, sort of the layout of how that works. But it really makes installing, when you're putting a lot of probes at one site, it makes it a lot easier. And if you dealt with programming SDI 12, you know what I mean.
Well, and I guess I'm just a little concerned when you press that button and it reprograms all the SDI 12 addresses, how you keep track of what it's doing at that point. But I'll talk to you offline about that.